Welcome everybody to Theory Lunch. Today our speaker is Raj, and he'll be telling us about an improved analysis of the quadtree for high-dimensional Earth mover distance. So take it away, Raj.
Thank you. So yeah, I'll be telling you about this old algorithm, but a new analysis for a classical problem called Earth mover distance. And the algorithm is, of course, this quadtree algorithm. So this is a joint work with Shi Chen, who's a professor at Columbia, Amit Levy, who just graduated from Waterloo, and Eric Weingarter, who also just graduated from Columbia and is now doing a postdoc at Stanford. Isaac, do you mind muting your mic? Thanks. Okay. Cool. So the promise I have, there's still some noise. Oh, okay. That's Greg. All right.
I'm sorry, guys.
No worries. Okay. So the promise I want to give you guys, and the goal of this talk is that by the end of the talk, you'll love your classic algorithms textbook, your CLRS algorithms textbook. And the reason for that is that what we're going to do is we'll go through the different chapters of CLRS, and we'll see how they apply to this classical Earth mover distance problem. And I'll begin with a non-standard chapter, which I'll call chapter 0, which is going to be introducing this problem, this classical Earth mover distance problem. So Earth mover distance is it's a metric, and it's a sort of a meta-metric in the sense that it computes distances between sets of points which live in a metric space. So given some metric x and dx, some distance on that metric space, the Earth mover distance is defined between pairs of multisets A and B, where A is some set A1 up to AN and B is some set B1 up to BN, both living in the same metric space X. And these sets have to have equal size for this talk. And so what is the Earth mover distance? Well, the Earth mover distance between A and B is just the cost of a minimum matching, perfect matching between the points in A and the points in B, where the cost is evaluated by the distance in the underlying metric. So in other words, it's the minimum over all bijections from the points in A to the points in B of the cost of that bijection or matching, which is the distance between each point AI and the point B pi I, which is matched to in the underlying metric space. So the goal of the Earth mover distance problem is to compute a good matching that's either optimal, either it satisfies it's the best possible matching, or it's close to optimal. So we want to find a matching M that is a bijection from the points in A to the points in B, such that the cost of that matching, which is the sum of the distances between AI and the points that they're matched to, BMI, we want that to be either optimal or close to optimal. So close to optimal would be at most an alpha factor larger than the optimal Earth mover distance, where alpha is some factor greater than 1. And for this talk, we're just going to fix some matching OPT, which will be any optimal matching between the points in A and the points in B. So the cost of opt is the Earth mover distance. So let me just begin by a little bit of motivation for why we would want to study this problem. So this problem is actually, it's been studied for a number of different applications. And classically, Earth mover distance was studied quite a bit on the plane, because on the plane, you could use Earth mover distance to represent a similarity between images. But for high dimensional Earth mover distance, which this talk is focused on, there's actually a very compelling motivation and very fruitful motivation coming from natural language processing. In particular, this idea of the word mover distance, which was introduced in this paper of Kuzners, Sun, Kulkin, and Weinberg in 2015. And the idea behind this paper is to use Earth mover distance to measure similarity between documents or sentences. So I'm going to give you an idea of how that's done here. So we can see you have two sentences. Obama speaks to the press in Chicago, and in Illinois, the president greeted with the media. So these are two sentences which maybe syntactically and in terms of the words that are used, they are almost completely different. There's nothing in common. On the other hand, you can sort of tell as a human that they're representing pretty much the same thing. They're trying to say the same thing. In particular, if you tried to think about matching up the important words in one sentence to the important words in the other sentence, you could notice that Obama is very close to the word president under some understanding of what these words mean. I mean, at the time this paper is published, Obama was the president. Chicago is in Illinois, speaks is similar to greeted, and press is meaning the same thing as media. So there is some matching between these words, which if you could show that two words were similar, you could potentially use Earth mover distance to notice that these sentences are saying a similar thing. So what is the magic trick to allow us to actually use Earth mover distance? Well, it's these, what I think are somewhat magical things called word embeddings. So you may be familiar with things like this. One example is word to vec or glove. And what these do is they take words like Obama speaks or Chicago, and they map them to high dimensional vectors in RD. And the promise, that sort of the hope of these word embeddings, is that similar words like Obama and president will map to similar points in high dimensional space. So here is the picture from that paper of Kozner, Sultan, Kolkin, and Weinberg. And you can see it, if you actually, after you compute these word embeddings, Obama does indeed map to something close to president, speaks maps close to greeted, and so on. So similar words map to similar spots. So then to determine how similar these sentences are, you have vectors lying in R dimension and D dimensions. You really can just apply the earth mover distance. And so what they do is they first take their documents, they apply a word embedding, and then they use earth mover distance to determine how similar the documents are. And this has been a very influential idea in NLP and related areas for high dimensional earth mover distance. So this is I think one of the main motivating factors for high dimensional earth mover distance, but there's a number of others as well. Okay, so now we're going to move on in our CLRS textbook to the next chapter. And this will be the first classical algorithmic framework for attacking a problem like this. And this will be the graph algorithms framework. So remember, this earth mover distance problem, it's really just a bipartite matching problem. I have some blue points, I have some red points. I can match any pair of them, and the distances are given from this underlying metric space. And I want to find the minimum cost perfect bipartite matching. So to do this, there's actually a very classical algorithm known as the Hungarian algorithm, which will solve this problem in n cubed time. If you have n points in A and n points in B in the sets, you can find an optimal matching in n cubed time. And so this is a classical algorithm. It's known since the 1950s, this paper of Emmons and Cart. But I actually recently learned that this Hungarian algorithm was known almost a century earlier. I guess it was in some unpublished notes of Jacobi in the 1850s. So this algorithm is somehow a fundamental and important algorithm that's been around for a long time. But if you can actually do a little bit better for this exact solution for general earth mover distance, and that's by noting that you can model this as a min-cost flow problem. And then there's some recent, very fast solvers for these min-cost flow problems. For instance, this paper of Lee and Sidford in 2014. And this will give you a solution in n to the 2.5 time. Unfortunately, if we want to get a perfect matching, the best matching, it's unlikely that we could do it much better. In particular, there's some hardness results, this paper of Rigatti in 2019, that shows that under a very common assumption called the orthogonal vectors conjecture, no algorithm can give you optimal matching in less than quadratic time. So if we want efficient algorithms, and this point of this talk will be to study mainly efficient algorithms, we're going to have to settle for some approximations. So the next step before we actually introduce this Quadtree algorithm is to try another classical algorithms framework for attacking these problems. And that'll be the greedy algorithm. So this is chapter 2 of our textbook. And greedy algorithms are a natural framework. What happens if we just try to greedily match up points? What will we get from that? Like we find the pair of two closest points, match them, and continuously do this. Well, it may not be difficult to guess that this actually is a fairly bad algorithm. In particular, a paper of Reingold and Tarjan from the 80s shows not only does this give a polynomial approximation factor, like it gives an n to the 0.584 something approximation to the optimal solution, which is pretty bad because there's an n in it, but actually this is also tight. So this is actually the approximation factor which is given by the greedy algorithm. And this is even in a very simple metric space, just on the line. So this is a very interesting result, which says that greedy is pretty poor, even for very simple metric spaces. But one thing that I want to note, and this will hint at the approach that Quadtree takes, is that actually for certain kinds of metrics, there is a greedy algorithm which is in fact optimal. And this is the case for so-called tree metrics. So what does this mean? Well, suppose I have some tree and my points are just vertices in this tree. For example, I have some blue points that are in these vertices and I have some red points. And my distance metric is just the shortest path metric on this tree. Well, then it turns out that there actually is a greedy matching, just the so-called bottom-up greedy matching, which we'll see in a moment, which is optimal for this tree metric and will give you the optimal earth mover distance. And the idea is pretty simple. I just take all my points at the bottom level and I push them up one level. And then I see any points that are now in the same vertex, and then I just arbitrarily match them up. For instance, now A is in the same vertex as X and Y. So I can choose to match A to either of these 2 points, and I can choose to match Z to B. So I'll do that now, and I'll match these 2 points up. And now I'll push the points up one further up the tree, and now I have, these C, either C or D can be matched to W. It doesn't matter which one I choose. I'll arbitrarily match it. They were at a distance of 3 in the tree. And then I'll keep going until I've matched up all the points. And at this point, I'll have a matching, and it's not, a simple proof strategy is using the standard greedy proof technique to show that this is an optimal matching. So this is something to keep in mind as we think about trees in the subsequent slides. So now I'll move on to an important chapter, which is the third algorithmic framework for attacking these kinds of problems, and that's the divide and conquer strategy. And this is the important one because this is the one that Quadtree will actually fall into. So Quadtree, the algorithm of this talk, is going to be a divide and conquer algorithm. And I'll note now that I'm going to fix for the rest of the talk the metric space that we're going to work with for just being the hypercube. So 0, 1 to the D-dimensional hypercube. And the distance I'm going to consider is just the L1 or Hamming distance. So the distance between 2 points is just the number of bits where they differ in the hypercube. And I want to mention that the reason we do this is because it makes it a lot easier to state the results and to state the algorithm. But there's some standard embeddings. If you have points in D dimensions, they don't need to be in the hypercube. You can always embed them with low distortion, even if they have like the Euclidean distance or an LP distance for P between 1 and 2, say. You can always embed them into the hypercube. So we're not really losing generality here by doing this. But for now, we can just think of the hypercube. So the Quadtree algorithm that we'll be discussing fits into this very large class of methods known as randomized tree embeddings. So this is a very fruitful and successful class of methods, going back to this paper of Bartle and even before then, for attacking these geometric problems. And I'll note that I think, to the best of my knowledge, it was first used for earth mover distance in this paper of Charikar from 2002, and then later by Indyk and Thaper. And what they showed is that Quadtree, this method of randomized tree embeddings, gives a linear time algorithm for giving an approximate solution to earth mover distance. So linear, like if we have n points in D dimensions, the runtime is order ND. So it's a very fast algorithm, and it gives some approximation. And I'll mention, this isn't the point of this talk, but I'll mention that if you want slightly better approximations, there are some quadratic time algorithms which give slightly finer approximations to the earth mover distance. For instance, this so-called Sinkhorn method and these related methods from optimization. But we'll be focusing on this Quadtree algorithm, which is much faster, but gives slightly coarser approximations. And then one other reason why we study the Quadtree in these kinds of randomized tree embeddings is that they have a lot of nice properties. And one of them is that they often yield so-called sketching or streaming algorithms. For example, if you saw the points in a stream and you wanted to compute the matching in small space, you can do this with these, usually with these randomized tree embeddings. Whereas these other methods like the Sinkhorn, it's not clear that this is possible. So what is a randomized tree embedding, and how does this relate to earth mover distance? Well, I think it's actually a very simple high-level idea. The idea is we have these points living in the hypercube. So what we're going to do is we're going to recursively divide up the hypercube. We'll split it and then recursively continue splitting it and splitting it. And this recursive division will create a recursion tree naturally. And this recursion tree, we'll call it T. So we have a tree T, and we'll take our points in A and B, and they'll get mapped to vertices of T, depending on where they went in the recursion. So when we split up space, the points go to the part of space that they were mapped to. So now we've mapped our points to this tree. And now we saw earlier that given a tree and some points in a tree, a good thing to do might be to greedily match them up in the bottom-up fashion. And so that's exactly what we'll do. We recursively partition space, map the points into a tree, and then greedily match the points up in the tree. And that will give us the matching. That's actually the entire algorithm. But why is this maybe a good idea? And the intuition comes from this line of work relating to locally sensitive hashing and things like this. The idea is that if I have points A and B, which are actually close in the hypercube, then they're less likely to be split up by one of these space partitions. So if they're less likely to split up, we hope that they'll stay together longer down in the tree. And then when we do the matching, they'll be more likely to be matched together. On the other hand, if we have points that are far away from each other in the hypercube, we expect for them to be split up in one of these cuts early on, and then they'll end up in different subtrees far away, and then they'll be less likely to be matched in the matching. So this is the idea. Close points should stay together for closer in the tree. Far points should be split earlier on, higher up in the tree. So this really is the entire algorithm, but we're going to instantiate it. Actually, sorry, I'm going to first tell you what was known for this simple algorithm. For earth mover distance, this algorithm, it's a linear time algorithm. It was known that it gives a log n times the minimum of log n and log d approximation to the optimal cost of matching. And this is from a paper of Andoni, Indyk, and Kraftgammer, and then also recently Baccaris, Dong, Indyk, Rasenstein, and Wagner. Basically, both of them gave one part of this minimum here. So the main result of our work is to show that the same algorithm, the same classical framework, actually gives a much better approximation factor. In particular, we show it gives a tilde O of log n approximation, where this tilde is hiding a poly log n factor, actually a log squared factor. So in particular, we show that actually no dependence on the dimension, well, this is already known, is needed even if the dimension is comparable to log n. And you don't need the second log n factor. So if these two things are comparable, it's roughly a quadratic improvement. And also, it's not too difficult to see that this is tight for Quadtree, that this class of Quadtree algorithms of recursive space partitions will need to pay a log n factor for their matching. And I just want to state, like, sort of the main takeaway message that we'll see is that the improvements, and the reason we were able to obtain these improvements is by somehow considering an average case notion of distortion in these randomized space partitions and tree embeddings, whereas earlier sort of a worst case bound was considered. And we'll go into that in a bit. But now I'll get to the slide that I was going to mention earlier, which is telling you how you actually implement this in the hypercube. We're going to recursively split up space. So how do we split up space? That's what I'm going to tell you on this slide. And we're going to write this down as a divide and conquer recursive algorithm, as I promised. So how does it work? Well, Quadtree is given as input two sets, multi-sets, A and B, in the hypercube. Because this is a recursive algorithm, we're not going to assume that A and B have the same size at this call. So what Quadtree is going to try to do is it's going to try to match up as many points in A as it can to B. But because these sets need not be the same size, A could have more points than B. So if A has more points than B, I'll match up as many points in B to the points in A, but I'll have some extra points left over. So what I'll return is actually some extra excess points that are unmatched. So the output is an A prime, B prime, where only at most one of these two is non-empty. And so if A is bigger than B, we return some A prime of unmatched points in A. If B is bigger than A, we return some unmatched points B prime in B. So that's all this output is saying. It's returning some points that weren't matched if one of the sets was bigger than the other. In particular, if A and B have the same size, these two will be empty. So how do we split up space? Well, probably by one of the simplest methods you could think of, which is we're just going to sample a coordinate I uniformly at random from the hypercube, and we're going to cut along that coordinate. So in particular, I sample this coordinate I, and I define these sets A0, A1, where A0 is all the points in A which have ith coordinate equal to 0. A1 is all the points in A which have ith coordinate equal to 1. And then I similarly define B0 and B1. So I split up the points depending on what their ith coordinate is. Now that I've done that, I can just make two recursive calls to the same algorithm. I call Quadtree on the ones that have a 0, A0 and B0, and I call Quadtree on A1 and B1. So I make two recursive calls on the ones and the zeros. The recursive call to the zeros may return some excess points which were unmatched in that call, if A0, for example, had a different number of points than B0. And a similar thing will happen over here. We may get some extra points which return from the second recursive call. So now we have some extra points here, some extra points here. We're just going to match up as many of them as we can. So we'll take all the points in A returned from this one, from A, and all the points returned from these two recursive calls from B, this B0 prime and B1 prime. These are just the excess points. And I'll just match up as many as I can of them as I can arbitrarily. And any leftovers, I'll just return in these A prime and B prime. So that's the entire algorithm. Just in summary, all we're doing is we have our points, we cut them along some random coordinate I, we match up as many as we can that are returned as excess, and if there's still some points which are unmatched, we send them back up the tree in the recursive call. So I think this kind of algorithm is easier to see with a picture, and so that's what I'll do on this slide. And here we have, these 4 points, these red points and these blue points that we want to match together. And on the right side over here, I'm going to construct the quadtree as it's being created with these recursive calls. So the idea is, and let's pretend that these points are actually living in the hypercube. Obviously, I can't draw the d-dimensional hypercube. So I'm going to sample some coordinate, and this will cut the points in half, depending on whether they have a 0 in that coordinate or a 1 in that coordinate. And then the points with a 0 go down the 0 subtree, and the points with a 1 go down the 1 subtree. And then I just continue recursively doing this procedure. I cut again, and this splits up the points further, depending whether they had a 0 or a 1 over here. And they continue going down the subtree. And then I just keep making cuts over and over again until in the base case, there's only 1 point in any one of these leaves. And this is exactly the same algorithm I described on the last slide. Finally, I have this tree here, and I have some points that are in the leaves. So I'm just going to do the greedy bottom-up matching we saw earlier. I'll just push the points up 1 level, and then I'll match up arbitrarily any of the points I can. So these 2 points can be matched, and some of these points can be matched. So right, okay, sorry, I went the wrong way. There we go. So we push the points up the tree 1 level. These 2 points can be matched. These 2 points can be matched. So we match them up in the tree, in the actual metric space. But then there's some unmatched points, and we keep pushing them up the tree until they can land in the same point, and then we decide to match them up. And this is how we get our matching, just the greedy bottom-up matching. So this is just the same algorithm I described earlier, but I want to take a moment to pause here to ask if there's any questions or clarifications I can offer for the algorithm before I get into the analysis.
I have a question.
Mm-hmm.
So when you're drawing the picture, it looked like at every level, it was the same coordinate for all the quadtrees. Was that just a drawing thing, or is that how the algorithm works?
That's a very good point. It turns out it doesn't matter. But you're right. On this picture, it looked like there was the same coordinate. On the last thing, it wouldn't have been the same coordinate because the recursive calls were independent. It turns out it doesn't matter for the analysis.
Okay.
And that's basically because the analysis is kind of going to kind of go by expectation everywhere. And so by linear, it's not going to matter for that reason.
Okay, thanks.
Okay, cool. So before I tell you about the analysis, I'm just going to make a slight bait and switch, but I promise it's a very minor bait and switch. And on this prior slides, the quadtree was sampling 1 coordinate at a time and then splitting into 2. So the quadtree would have been a binary tree. What I'm going to do here is I'm just going to compress some of the levels of the tree so that it's not so tall. And this actually isn't necessary from an analytic perspective. Actually, our analysis will apply to this quadtree as well, but it'll make it a little bit easier to present and also to talk about the analysis. So what is the compressed quadtree? Well, at depth j, instead of just sampling 1 coordinate, I'm going to sample 2 to the j coordinates, I1 up to I2 to the j, uniformly at random. And then I'll split into all possible ways that this partition that you can assign bits to these 2 to the j coordinates. So really all I've done is I've taken the levels j to 2j, and I've compressed them. I've taken the levels, the 2 to the j coordinates where I would have sampled I1 up to I2 to the j. Those are 2 to the j levels, and I've just compressed them into 1 level. So this is the same as a contraction in graph theory. I'm just compressing the levels. And as a result, I'll have, instead of 2 children, I'll have 2 to the j children. So the picture is, it's just simple. At the first level, I sample 1 coordinate, I have 2 children. At the second level, I sample 2 coordinates, I have 4 children, corresponding to the ones that have a 0, 0, ones that have a 0, 1, and then so on. And then I'll sample 8, and then 16, and then so on. So that's all I'm going to do. I'm just going to do this a little bit faster. So instead of d levels, I'll have log d levels. Because at the end, I'll have sampled all the coordinates in the tree, roughly, in the hypercube. Now, I'm gonna say something here, and I'm gonna try to justify why this is a good ideal. So here's gonna be the overarching goal of this entire analysis. It's that if I have 2 points A and B in the hypercube, and I'm gonna write A and B are in a vertex V of the tree to mean that A and B were in that vertex, that recursive call corresponding to that vertex in the quadtree. So suppose I have some vertex V that's at depth J of this compressed quadtree. If I have 2 points which are both in that same vertex, what I hope and what the ideal is the distance between A and B in the original metric should be no larger than d over 2 to the j. That's what I'm going to hope for. And so why is this a reasonable thing to ask? Well, note that at depth j, I would have sampled 2 to the j coordinates roughly at this point. So if I've sampled 2 to the j coordinates, and if the distance between A and B is much larger than d over 2 to the j, then I expect to sample one of the coordinates where A and B actually differ at this point. And if I did that, then A and B would have no longer been in the same vertex. They would have been sent to different recursive calls if I sampled one of the coordinates where A and B differed. So if A and B are still together at depth j, we expect for them to be no more than distance d over 2 to the j together. And so under some loose definition of what it means to, we expect them to not be together. So this is the ideal. But what is the worst case? Well, unfortunately, it turns out in the worst case, you can have 2 points which are together at depth j, but their distance is a log n factor larger than what we hoped it to be. It's log n times d over 2 to the j. So this is a worst case bound which can occur in the quadtree, despite the fact that we want them to be split by this point.
So Raj, it's a worst case, like with high probability or something like this? You're taking
Yes, with high probability, yeah. And it's easy to see this because if every time you sample, at this point, I'm going to sample 2 to the j coordinates. And so I expect to see at least log n coordinates where A and B differ. So with high probability, I'll see at least 1 and then split them. So here's going to be the main thing that I want you to take away from what the new idea is. Somehow in earlier analysis, they said that this could always happen. We always pay this log n whenever we are in the quadtree. We're going to show that while this can happen, it cannot happen too many times in the quadtree. And this is how we're going to get our improvements. So now we're going to move to one of the final chapters, and this is chapter 4. And I want to just, there's not a whole lot of people in the audience, but I want to open it up to guesses based on this proof strategy, what the chapter of CLRS that describes this, this proof strategy that I just defined. So we want to show that this worst case can't happen too often. On the whole, it won't happen.
Potential functions?
I think that class that qualifies. We're going to go with amortized analysis. So I think potential functions are a way of doing amortized analysis, if I remember correctly. So we're going to show that this can't happen on the whole too often. But what we're actually going to call this is something slightly different. We're going to call this the inspector analysis. And the reason is it's a kind of amortized analysis, but maybe it's a slight riff off of this. And the idea that we have in mind is you have some inspector who's watching the quadtree, execute, and the points going through the quadtree. And the inspector has total knowledge of the optimal matching and whatever else knowledge you want to give him. And what he's going to do is, instead of analyzing the cost of the matching produced in quadtree directly, the inspector is going to come up with some payment scheme based on how the points split. This is kind of the amortized analysis idea. And this payment scheme is going to be enough to cover the costs of the matching. So it's a coupling between the payment scheme and the actual cost of the matching. And then instead of bounding the cost of the matching, we'll bound the inspector payments instead. And this will allow us to, by transitivity, bound the cost of the matching. And the crucial difference here is that the inspector payments are going to be 2 things. They'll be data dependent. So the inspector will look at where the data goes and pay different costs depending on where the data goes, instead of a fixed cost for every level of the quadtree. And this is going to somehow, the goal will be to capture some average case notion of distance between sets of points in the quadtree. So the first idea is this idea of average case distortion, which is actually going to be kind of a simple thing to state. But to do that, I'm just going to introduce a couple pieces of notation first. So remember that for every vertex in the tree, we mapped it from the root of the tree. So for every point A, we mapped it down this path from the root of the quadtree down to a leaf during the execution of the quadtree. So that means that every point A gets a path from the root to the leaf associated with it. So it makes sense to define the jth vertex along this path. So we write v sub j of A just to be the vertex that's at depth j that contain this point A. And now that we've done that, we can say for any vertex in the tree, we can define big A sub v to be all the points in the set A which went through that vertex v. So A sub v, and then we can similarly define B sub v, are the sets of points which mapped through that vertex v. And now what I'm going to do is I'm just going to define the center of mass of a vertex. The center of mass is actually just the center of mass. So if I have a vertex v in the quadtree, I have some set of points AV and BV which map to that vertex. So the union of AV and BV are all the points which went through that vertex. So the center of mass of these points is just the sum of all the points divided by the number of points that there are. It's actually just the average. So the pictures, you have some circle here. These are all the points which map to some vertex. I have some ones in blue and some of the red, and the center of mass is just somewhere right in the middle. It's the average. And so we'll be following the center of mass and using this to construct our payments. So now I can tell you what the inspector payments are. It's it only depends on this idea of center of mass. And so what the inspector is going to pay is the inspector is going to pay some quantity for every point A in the sets. So for every A, let B be the point which is matched to in the optimal matching. And remember, the inspector knows this. It's just the analytic technique. So we're going to define pay of A to be the following quantity. We're going to look for the first time in the tree where A and B are split apart from each other. At the first moment where A and B are split by some level J in the tree, we're going to start paying some quantity, which is the distance from A to the center of mass at the vertex where it is. So we don't pay anything until A and B split. And once they split, we pay the distance from A to the center of mass of every vertex down the tree that it shows up in. So the picture looks like this. I have some vertex up here that contains both A and its optimal matching B. But at this vertex, they actually get split. A goes down the left subtree and B goes down the right subtree. So when this happens, I need to start paying. So I'll pay the distance from A to this center, and I'll pay the distance from A to this center, and then so on, all the way down the tree. And then pay B of T will do the same thing, paying from distance from B to the center and B over here. So this is the entire payment strategy for the inspector. And he'll pay this for every point. So what is the first thing that we want to show? Well, we want to show that the inspector is paying enough to cover the cost of the matching that we're trying to bound. And so this is exactly what this relatively simple proposition states. And it's not too hard to prove this. And the idea is kind of just by multiple application of the triangle inequality. So what we're going to show is that if you sum over all the pairs and the optimal matching and look at the payment that the inspector pays for A and B times maybe a factor of 2, this covers the cost of the matching produced by Quadtree. And so the idea is, the way you show that this is enough to cover it is you take all the points at the bottom of the tree and you move them to their center of mass. And then you keep moving them from center of mass to center of mass along the tree. And whenever points can be matched up, they can be matched up in the center of mass. And by triangle inequality, the sum of these distances bounds the cost to move them together. And the idea is that if you have some points which are unmatched, which need to move from one center to another center, that means there must have been at least that many points which are split early by that point. So you can pay enough to move them from one center to another center all the way up the tree. That's just the high level idea of how this proof goes. But this shows that this payment scheme is enough to cover the cost. So what we need to do is just upper bound this cost. And that will be how we complete the proof. We just need to show this is not too large compared to the Earth mover distance. So now here's my plan. I'm going to tell you how we could bound this with a first strategy, and we'll see how it kind of recovers the worst case distortion from prior works, and then we'll see what the crucial new idea is. So what is this worst case bound? Now remember, our payments are somehow tracking the distance from A to the center of mass at the vertex that A hashes to at level J. So what is the expected distance? Well, remember, we wanted these distances to be at most d over 2 to the j. That was our ideal. But it turns out even the distance to the center of mass can be much further away. It can be a log n factor times larger. And the reason is kind of similar to the answer to Anupam's question earlier, is that there's a very simple fact that you can prove, which is that if I have 2 points A and B that are at distance, say, alpha times larger than d over 2 to the j, say alpha is greater than 1, then the probability that they stay together at level J, we want them to split if they're too far apart. The probability that they stay together is 1 over 2 to the alpha. This is a fairly easy thing to prove, but what it says is that if you set alpha to be log n, the probability that 2 points are, like, say, 10 times log n factor larger than d over 2 to the j, and they're still together at level J, is at most 1 over poly n. So by a union bound, no pairs of points will actually be together at level J that are a log n factor larger. So not only do we have this worst case bound, but actually no pairs of points will collide at this distance larger than log n times d over 2 to the j. So this is the first bound. And now for any point, we need to remember we only start paying this cost once A and B split in the optimal matching. So let's look at A and B, any A and B in the optimal matching, and suppose their distance is d over 2 to the j, or some j. Now the issue is that they may split earlier on in the tree. We would like them to split at level j, but they could split early. And if they split early, we start paying more in this payment cost. So in particular, for every value k, we could split k levels early. And so the probability that you actually split these 2 points, split k levels early at level j minus k, well, it's not too hard to show that this is at most 1 over 2 to the k. But if that happens, if they split these k levels early, we're going to have to start paying this cost k levels early. And this cost will be roughly a 2 to the k factor larger. So if we split, k levels early, we may pay a 2 to the k factor more. So how do we put this all together? Well, okay, suppose we have a pair A and B that are at distance d over 2 to the j. What is the suspected payment? What can we bound it by? Well, we've already basically done what we need to do. We pay summing over all the levels where we could split early. And we don't need to sum over the lower levels because it turns out that these levels don't contribute as much. They contribute a geometrically smaller amount. This is the probability that we split k levels early, 1 over 2 to the k. And this is the expected distance from A to the center of mass. I'm being a little bit loose here because there's some conditioning issues, but let's not worry about that. We just showed that this is always at most log n times d over 2 to the depth, which is j minus k here. So these 2 to the k's cancel. And we just get log n times d over 2 to the j, which was the distance between these points to begin with, d over 2 to the j. So this is log n times the distance between the points summed over all possible levels where they split early. There's at most log d levels in the quadtree, so we get log n log d times the distance between the points. And so this is actually going to recover the bounds that were already known. In particular, if I just sum this over all the points, this says that the total cost paid by the inspector is at most a log n times log d factor larger than what the actual Earth mover distance is, the sum over all the pairs in the optimal and the distance between them. So the reason I wanted to go through this worst case analysis is to show you where is this extra log d factor coming from? And the idea is that in this quadtree, we had log d chances for optimal pairs to split early. And what we said is that anytime they split early, they're going to pay a log n factor. And they're going to have to pay this log n factor to move together. And what we're going to show, as I hinted, is that while this can happen, while there may be some levels where if A and B split early, the distance for them to their center of mass will be a log n factor larger, we're going to show this can only happen log n times instead of all log d times. So there's log d chances to split early, but only log n of them can be bad. And this is how we're going to save this factor of log d. Okay, so actually I'm a little bit ahead of time. So are there any questions about what I've said so far before I move on? The next series of slides has the key idea. So before I do that, I want to questions. Okay, so if this was a little bit too fast and if you missed this, that's totally all right, because the next couple of slides I'm going to explain the new idea, and I think that it should hopefully be clear from a picture. So I'm just going to restate what I said now a bit more formally. We have some point A, and we want to measure how far do we expect it to be from its center of mass. And we know, as I've said several times, we can still sometimes pay this worst case bound where it's a log n factor larger than d over 2 to the j. But what we're formally going to show is that for any point A, there's at most log n levels of the tree where this can occur. So for any point A, you look at all the levels of the tree, and only a small fraction of them, of the log d levels, can actually be, A actually be that far from the center of mass in expectation. So this is just going to be a couple of slides, which I think will totally capture the proof idea, because I think it's a somehow not a very complicated proof idea, but it's best shown by a picture, I think. So this is actually going to be an example. So suppose we have some point A here. And let's suppose we're looking at a vertex that's at depth j. So again, what our ideal is that hopefully A should be at distance d over 2 to the j points. d over 2 to the j from the points that it matches with in here. Unfortunately, let's see, maybe it pays a log n factor more. So maybe the distance between A and the center of mass is like log root n d over 2 to the j. Just as an example, this is like 1/2 log n. So this is a bad vertex because A is far from the center of mass. But if A is far from the center of mass, then there must be at least some point that was also far from A. Otherwise, the center of mass couldn't have been far away. Okay, so there must have been some point P here, which was also at distance at least log root n d over 2 to the j away from A, for the center of mass to be that far. But remember, A and P collide with very small probability because they're a log root n factor far apart, the probability that A and P actually did end up together is 1 over root n, because it's 2 to this factor, whatever factor larger you are here. Okay, so, but even though it's really low probability, it did collide. Some point P did actually collide. So if that was the case, then we expect that there must have been at least root n points which were at the same distance of log root n over d over 2 to the j, which didn't collide. If I have, a bunch of trials and each one of them succeeds with probability 1 over root n, and some of them succeed, like 3 of these trials succeed, I expected there to be at least root n points which had an opportunity of being sampled. Otherwise, I wouldn't have expected to get any points here. So what this says is that if I had a center of mass which was far, there must have been at least one point which was far. That point survived with small probability, 1 over root n. So there must have been many more points just outside which didn't survive, which had an opportunity to survive. Okay, so that means I have root n points over here which are not too far away. They're at distance log root n over d over 2 to the j. So now what I'm going to do is I'm going to walk a couple levels up the tree. I'll walk log n levels up. And at this point, I expect that all these root n points which were far will now be contained in this new vertex u at depth j minus log n. So I've just stepped log n levels up the tree to a new vertex u. These root n points should now all be contained in the same vertex as A, because that's how corresponding to how far they were. Moreover, these points will now be close points. They'll be in line with what the distance I wanted A to be at distance u, so d over the depth of u. But now let's assume that a bad thing has still happened, that the distance between A and the center of mass is still far. And note we have these root n points, but maybe we picked up some more points. These root n points were close, but if the distance from A to the center of mass was still far away, say again log root n factor larger than it should have been, which is d over 2 to the depth u, then what does that mean? I had root n points which are close, but the center of mass is an average. So I must have had root n points which are also far to pull the center of mass far away. So there must have been root n points over here which were very far away, which pulled the center of mass far away. But again, the same game is going to happen because each of these points all the way out here only survive with probability 1 over root n. And if root n of them survived, then there must have been n points just outside which didn't survive. And you can keep playing this game, but note that at this point, we can't keep playing this game because we only have n points. So at this point, I can't keep increasing the size of the thing because I've run out of points. So the moral here is that if the distance is really far to the center of mass, that must be because some points survived that were far, which means that there are many more points which didn't survive. So the size of the number of points around you needs to be growing exponentially. Like many more points need to be growing. So every time you are log n factor larger, you need poly n more points around you. And so this can only happen a small number of times. So that's basically the entire idea of how you prove this. And I'll formalize it on this slide, what we showed. We showed that, let this be AR, let's just define this to be the ball of radius r around A, intersecting points that we care about. So this is just, you have some point A, and you're looking at all the points that are at distance at most r. What we just showed is that if the expected distance from A to the center of mass of B for some depth j is an alpha factor larger than it should be, then we show that the number of points which are at that distance, alpha over d to the j, grows by a 2 to the alpha factor larger than it was at the last level. So if you're an alpha factor, if the expected distance is an alpha factor bad, you have 2 to the alpha more points. And so this shows roughly doubly exponential growth every time you have a bad level. And so as a result, you have only poly log n bad levels. And this allows us to show that the expected payment cost is only a tilde log n factor larger than the actual distance between A and B in the quadtree. And so by linearity, the total inspector cost is log n times the earth mover distance. And this is the main idea of the new proof. Okay, cool. So that's actually the key idea I wanted to get across. Are there any questions about that the strategy and what was new here? Cool. I want to end because there's actually a bunch of open problems here. So this complexity for offline algorithms estimating this earth mover distance for Quadtree is tight for this Quadtree algorithm. But there's a number of things that we don't know how to do yet. One of them is this so-called Wasserstein 2 distance. So the earth mover distance is actually a certain kind of metric called a Wasserstein metric. And in particular, there's these Wasserstein P metrics. And if you set P equals 2, you get the Wasserstein 2 distance. And that's just the same thing as earth mover distance. But instead of summing over the distances, you sum over the squared distances. So if you're familiar with clustering, for example, this is kind of like K means, whereas earth mover distance is like K medians. So, and in general, you could put a P here, and you want to minimize the cost when you have P. So Wasserstein 2 is much more sensitive to far points because you're squaring the distances. Unfortunately, because of that reason, it's easy to see that these randomized tree embedding approaches like Quadtree, they won't work for getting good approximations to the Wasserstein distance. Because when you split early, that event doesn't contribute at 2 to the k factor more. It contributes as 2 to the k quantity squared factor more, because you're squaring the contribution of those levels. So things don't cancel as nicely, and actually you don't get good expectation. So there's actually a pretty open problem to get like a linear time approximation algorithm which is efficient. I mean, good approximation for Wasserstein 2. Another question is, as I mentioned, is if you can get efficient sketching or streaming algorithms for this problem. I didn't formalize this, but in the paper, one of the main results is that we actually show that this new idea of this inspector payment instead of a tree embedding payment can be actually accomplished in a stream. So in a stream, that means I see the points in the hypercube one by one, and I'm told whether they're an A point or a B point. At the end, instead of outputting an actual matching, I want to output an approximation. Like I just want to tell you what the cost is, like how big the cost is. And I want a tilde O log n approximation of that cost. It turns out that we can show how to do this in 2 passes. So if you get to see the points twice, we show how to improve, get this new approximation factor in a 2-pass algorithm. And if it turns out, if the points, the sets A and B, don't overlap too much, in particular, if the size of the intersection compared to the size of the union is bounded away from 1, then we can give a 1-pass streaming algorithm for earth mover distance in small amount of space. But removing this assumption and getting a general, getting this new approximation factor in 1 pass, this is still open. And actually, there's lower bounds for streaming algorithms that show that this log n is probably the best you can get for a streaming algorithm. So this is sort of a big open problem which has been worked at for a while in the literature, and I think it'd be really interesting to show if it's possible to get this approximation in 1 pass. And similarly, to get anything like this at all for the Wasserstein 2 distance, that would be fantastic, but it seems challenging to do. So yeah, that's all I wanted to talk about, and I'll end with the final page of our textbook. And if there are any questions, yeah, feel free to ask. We have some time. Cool.
Hey Raj, so is there a reason to believe that you're losing those polylog-log factors, or is just that an artifact of your proof?
I think the proof is kind of limited at getting at least 1 log-log factor. I think you could there's like some bucketing you could do to save 1. So we have 2 currently log-log factors. There's some bucketing you could do to save 1 of them. Mm-hmm. But like, for example, if we go look at this picture here, I sort of need these points later on to be contained in the big set so that they show that the size of the thing is growing. But I won't get many of them until I walk up at least log n levels up the tree. So if you have like 1 bad level, it can make the next log n levels also bad. but just by what the definition of bad is. Like if bad says that your distance is a log n factor larger, then kind of the next like 1/2 log n levels will also be bad, just by definition. So maybe you don't need to pay. You probably don't need to pay this actually, but the proof strategy is kind of limited in that way by what the inspector is paying. If I had to guess, I would say that the cost, the amount of money that the inspector is paying, does pay this extra log n, but that doesn't mean that the matching does. Cool. Well, thanks everyone for coming.